provide data in high speed, and then a memory also need to work in the same way. So when we make these connections, this connection, or also in other blocks of any system, if we make connection or any other block, something like that. So what will happen that you need to you cannot directly connect with a wire. What you need to do is you need to put a proper transmitter here and a receiver here. Okay, so in general, what kind of transmitter and receiver should we put here? Okay, so the answer of this question will be like because processor will provide data to the memory. So uh, let's assume that we have data in maybe data 1, D1, D2, D3. So we have 3 data lines, and so we want that RAM should also, or any other building block should also receive the same data, D1 in the same form. But if you try to send it directly by connecting all of them, then it will unnecessarily take a lot of space, because you need to put a lot of metal lines. Okay, so the best way would be that you combine all of them in one place and then transmit, and then again you can open it here. Okay, so then the what so it looks very simple. So what can be the problem so what kind of challenges we need to face? So the first thing that the challenge we will face is, suppose this data is of 2.5 gigabit per second. So similarly, all the data, let's assume, is 2.5 gigabit per second. So when you combine, then let's assume this is how it is. Earlier it is like this. Okay, maybe like this. So it is D1, D2, D3 and D4. So when you combine all of them, then in the same period you need to put all this information. So the time period will remain the same, but you will put it in form of like this and send. So it is like that. If look at 2.5 gigabit per second, so you need to multiply it by 4, and here the total the transmission rate will be 10 gigabit per second. And again you will demux it and again get 2.5 gigabit per second data rate here. Okay, so the challenge would be that this interface block in transmitter side and in receiver side, both should be operating in high speed. Okay, and this data alignment, because here we are aligning the data, so this data alignment should be proper. Otherwise you will receive a false data at the receiver side. Okay, so we know that in general whenever we combine, so we use mux, okay, in digital domain. So ultimately what should be the transmitter? It should be mux, and suppose 4 lines are coming, and you need to have a clock. Okay, and here you should have demux, and it will give you all 4 data here. Okay, so now this clock cannot be normal clock, because the normally the if you, in general, we can generate sinusoidal signals using oscillators. So let's take VCO, voltage control oscillator. So this is not going to work. Okay, so you need to have pure clock here, so that the data, there is no phase variation in the data. So that is why you need to have phase lock loop that is connected here to provide a clock to mux. Okay, so now at so this is first challenge, that we need to design a good PLL. Okay, so that you can provide a clean clock to the block, and this mux and demux should be high speed. Okay, so they both should operate in 10 gigabit per second data rate, even if the data is 2.5 gigabit per second. Okay, so this is first challenge. Another challenge would be that, as I have told, the data, there should be data alignment. Okay, so it is called data retiming circuit. So we cannot simply put mux, we need to retime it so that the alignment is should be proper, and it appears to be proper at the output. So here you have data retiming circuit. Okay, so okay, so now we have data retiming circuit, then mux, and then demux. Then we know that this line, the interconnect, will act as a transmission line at such high speed. Okay, so you should know the characteristic of this transmission line. Okay, and during when you are designing the such system, then you should first characterize the transmission line, get its parameter, and use them during simulations when you are actually designing mux. Okay, so this transmission line characterization is required. Okay, apart from that, it is 50 ohm edged, so you need to put another block here. Okay, that will act as a buffer also, and 50 ohm matching also. You can say that buffer to drive this transmission line plus 50 ohm matching combination. So there are various combinations possible, but to ensure 50 ohm matching is a must. Otherwise, there will be reflection, and the corrupted data will be received. Okay. Moreover, at the receiver side also, again you will have 50 ohm matching circuit. Okay, so now till now we have seen that we need to have data retiming circuit, mux, PLL, and demux. But what will happen that when we characterize our transmission line, so we know its property, we know that ultimately it is going to work as a low pass filter. In general, we cannot say it in broad sense, but for circuit designing we assume that okay, there is some certain characteristic, and it is close to a low pass filtering action. Okay, when if we consider it as a RC line. Okay, so if this is we know that this is the characteristic of transmission line. So what we can do is what we can do is we can actually pre-emphasize the data, okay, at the transmitter side, so that better you can, it is like that, you know that there will be some corruption that will happen in the transmission line, and you are processing it in advance, so that that corruption of data can be compensated in advance level. Okay, so in such case, what we will do is we will put a block that is called equalizer. Okay, then matching, 50 ohm matching circuit. Okay, and then we have transmission line at the, or interconnect we can say. Okay, so this is data retiming. So now you can see the challenges in simple transmitter also, and here we need to design a PLL. So the equalizer that we will put here, so in general there are different kinds of equalizer, that some of the equalizers we put at the transmitter side, some of the equalizer we put at the receiver side. Okay, so in particularly this, in this transmitter side we put FFE, that is called feed forward equalizer. So we need to emphasize the data, and this is done by feed forward equalizer. So in transmitter side generally we put FFE, and in receiver side, because we received the data, so we need to process the received data. So at, so to get the better data, what you will do is you will put equalizer at receiver side also, and so generally FFE means it is digital kind of equalizer. So this FFE is digital kind, but at the receiver side generally analog equalizer is preferred. It is called linear equalizer also. Okay, and then in digital domain it is decision feedback equalizer. Okay, so there is another equalizer, that is decision feedback equalizer. It is in FFE it is feed forward based, in DFE it is feedback based. Okay, and then we have other blocks at the receiver side. Okay, so now we can see that and here we have demux. Okay, so and that will divide the data. Okay, so here everything looks fine, but the problem we will see at the receiver side is that even if we go for demuxing, we need to have a clock. Okay, and here you can see that we have only transmitted data, there is no clock. Okay, so what can be done? Either we can send a clock line with PLL to the receiver side, but the problem would be the challenges we will face if we do like this, that because of there is certain delay of transmission of signal in transmission line, so this misalignment will happen. Okay, because both will be in different environment, and because it is not possible to put it side by side, so PLL will be at some other corner and of the circuit, so the possibility that there will be a small change in phase, so that small change in phase results in the bad recovered data. Okay, so what can be the solution? So the solution of this problem would be that we will generate clock at the receiver side itself. So we will not take this path. Okay, we will not use this clock, and we will generate clock at the receiver side itself. And this is done by using clock and data recovery circuit. Okay, so now we will have, so here you can see that the challenges are like so this particular thing is transmitter. So in transmitter we need to design equalizer, 50 ohms circuit plus buffer, high speed mux, and data retiming also we need to do. Okay, and apart from that, in receiver side we again need to have a 50 ohm matching circuit, analog equalizer, decision feedback equalizer, and a demux. So demux can be flip flop, but we need to so the demux can be the part of clock and data recovery circuit, or we can recover the data first and then do demuxing. So both way it is possible. So let's assume that it is not a part of it. So now the DFE will give a data to clock and data recovery, and the recovered clock and data we will apply to demux. Okay, and then it will demux the data. Okay, so why so before moving further, so what is the need of analog equalizer? Okay, so let's assume that we have, so here what will happen, let's assume this is the data, something like this. Okay, so after processing up to reaching here, it will be not like this, it will be something like this because of finite rise and fall time and parasitic capacitance and resistances. So because of that there will be finite rise and fall time. Okay, and then the equalizer will pre-emphasize it to help it to send it to, using transmission line, and then again we will receive. So whatever we receive, even if after pre-emphasizing, after doing equalization, we are going to receive a very bad data. Okay, so so it is like, it is the ideal data. You have transmitted something like this and you received something like this. Okay, so this rise and this fall is different for each of the pulses. Okay, and then this is the challenge that we need to understand that where is 1, where is 0 in this particular waveform, and then try to recover it. Okay, that is why this equalization is very much required, so that at least the data should be in the form that it can be recovered. Okay, but there is another problem with clock and data recovery circuit, because as I have told you that we are going to recover the clock from the data itself. So let's assume this is the data. Okay, and the ideal clock should be something like this. Okay, this is what we want to recover. Okay, so here you can see that this recovered clock can only be recovered when you have information of edges. Okay, but it is not always necessarily be true that this data will have you can say that frequent 0 and 1. Okay, so the data density can be very poor, and there will be long 1 and 0 in your circuitry, something like this. Sometimes it will be like this, but sometimes it will be like this. So you can see that if this is the your data, then actually you will send it something like this, something like this. Okay, and the received uh, data may be something like this, very bad quality. Even it is very difficult to find where is 1, where is 0, and because you have long 1 and long 0. Okay, so to get rid of this problem, there is another thing that we do, that is called line coding. Okay, so before sending here after the mux, generally another block that is put here, it is called line coding circuitry. So this, the work of this line coding circuit is to increase the data density. Okay, so it, what it will do is it will convert this particular thing in frequent fluctuation of 1 and 0. Okay, there is continuous variation of 1 and 0, something like this. So it is like 8-bit 10-bit coding. So so the name, a name is 8-bit 10-bit or 64 66b. This is the line coding techniques. Okay, and there are different smaller techniques also, but this is the standard that is generally used. Okay, so what it does is like where it converts all 8-bit to 10-bit. Okay, so there will be a frequent fluctuation of 1 and 0, and at the receiver side they will again decode it. Okay, first they'll encode at the transmitter side, and then they decode at the receiver side somewhere. Okay, here. Okay, and this decoding and line encoding can be done in digital domain itself. Okay, so now you can see that there are various blocks. Those are compulsory. Those are compulsory and is needed and should be designed in very proper way. Otherwise, the recovered data will be corrupted. Okay, so now whatever. So now moving to the clock and data recovery circuit. So now you can understand that in all these, those all the blocks, those are available here. All are very challenging blocks. Okay, so but in particular this talk we are going to discuss clock and data recovery, and we will look what kinds of challenges we need to face, and we'll look the solution to get rid of them. So first problem would be that, as I have told you, that ultimately we are going to receive only single line. Okay, so let's assume this is the data, ideal data that we wanted to be received, but because of practical limitation we got something like this. Okay, so even if we recover the data, we want that the data should be whatever clock we will recover, the data middle of the data should be at the edge of the clock. Okay, it should be something like this. Okay, so this middle of the data should occur at the edges of the clock. Okay, whenever we work on clock and data recovery, this we need to ensure. Okay. Okay, and this is after the equalization. So I am assuming that I have received this kind of we have got the this kind of extracted data. Okay, and so even if we get this kind of, sometimes I will use this, but it doesn't mean that we are going to get this kind of data. This is ideal data, and actually the data will be much worse when we receive it. And even the clock is not like this square wave, the clock will be sinusoidal, something like this. Okay, and there is another thing that I think I missed to point out, that in general, even if I have written here mux and demux and equalizer is also kind of a digital block, and PLL, most of the blocks are digital. Okay, so one may think that, okay, if it is 1.8 micrometer technology or 180 nanometer technology, then actually I am talking about the voltage levels of 0 and 1.8 volt, that is ground and VDD. Okay, but it is not always true, because what will happen that when we go for high speed, then it is very difficult to get a high speed with this much voltage variations. Okay, so if in 180 nanometer also, if you are working up to 2 gigabit per second data rate, then you can use digital CMOS digital. Otherwise the circuit will be digital, but the logic will be CML that you need to use, current mode logic. Okay, beyond 2 gigabit per second data rate. Okay, so in CML logic, this particular voltage variation will not be like this. It will be only let's assume this is 0 and this is 1.8, so the variation will be something like this. It will be somewhere in between it. Let's assume 0.5, and this is 200 millivolt. So here it is varying from zero point 0.5 to 0.7 volt only, something like this. Okay, so this we need to interpret as a 0 and 1, this 200 millivolt variation. So you can understand that if this is 200 millivolt, so the chance when it close, you can say that when it is a bad data, then there will be hardly any you can say that logic, it is very difficult to detect this logic, because when it is bad data, then this variation of 0 and 1 can be as less as 50 millivolt. Okay, so recovering the data is a challenging task. Okay, so, and this can be understood generally by eye diagram. So let me just give you, because the eye diagram is a common term in high speed circuits. So let me introduce the high speed, this particular terminology. So let's assume this is 1. So let's assume this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So let's assume that these are the clock period of the data. Okay, so I have written all the clock period in the number form. So what you need to do if you want to find the quality of data, so let's assume because of bad quality, it has finite rise and fall time, something like this. something like this. Okay, so what you will do is you will take this 1 2 3 4 5 6 7 8 9 10 12 13 14 and take only single time period of clock period. So let's assume this is one clock period. Okay, so this is one clock period. So what you will do is you will take one first, so it will be something like this. Okay, and then take two in the same time period. So this is one, this is two, so you will take two. Okay, then take three, so again it will be overlap. Then four, so again it will be overlap. Okay, then five, so something like this. So we know that there will be no same rise and fall time for all of them. So if you put one above the other, you will see a finite rise and fall time each of them. So you will put all of them 1 2 3 4 5 6 7 8 9 10, all 1 to 13. You will put one above the other, so it will be something like this. Okay, so now if you see this carefully, so actually you have got something like this. So because of variation, and so different waveform will have different variations, so when you put one above the other, it will look like something like this. Okay, and I am talking of this thing when we have a little bit better data. Okay, so if you look it carefully, it looks like an eye. Okay, so that is why this is called eye diagram. Okay, and in this eye diagram, this is called eye height, and this is called eye width. Okay, and to know the quality, you need to find the jitter. So this variation of edges is called jitter, peak to peak jitter. Okay, and this is amplitude variation. Variation for logic 1, and similarly here you have amplitude variation for logic 0, but this eye height will give you a better way. So this eye height is generally taken at 50% of, or you can say that at mid of the eye. Okay, so this is the eye diagram. So this is also a better eye diagram. So I am talking about eye which is something like this. So this is the rise time and this is the fall time. So in general, in practical scenario, whenever you receive a data, the eye is like this. So it is very difficult to find where is eye. So here you can only see this much variation at the receiver side. So when you receive the data here, so this is the eye type that you receive. It is very bad quality, something like this, and then you apply a equalizer etc to make it wide open, so then it will be little bit better. And then we apply data and clock recovery circuit, so that we can actually get to know where is edge, where are edges, and what is eye height, what is eye, means it should be sufficiently high. So this jitter should not be it should be in permissible level. It should not be too high, too large that we cannot actually um, get the center point of the data. Okay, so So this can be the problem. So to detect, so how to detect actually clock and data now? So what can be the ways? Okay, so to understand that thing, let's look at the characteristic of data first. So can we further simplify this particular data equation? So if we write first this particular waveform in form of equation, then it should be represented in this way. It is going till n. Okay, and it will be bk. Maybe I write simply k here. Okay. Okay, so here this can be 0 or 1, so based on the data what it is, and this is the shifted version of it. So ultimately this data will be in the form of either a 0 1 or the shifted version of the first and samples. Okay, so either if we want to further characterize it, actually we can say that it is nothing but a simple waveform like this. Okay, so and in time domain we can say that it is a sync function, or let's find the power spectral density. So in power spectral density way, it will be, so it will be sync function because it is a pulse. Okay, so it will be, the nulls will be at 1 upon tb, 2 upon tb. Okay, and the maximum will be at tb. Okay, so here we can see that there are spectral nulls at multiples of fb. Okay, so how to process this? So the first in time domain, if we look, then it is quite simple, that we want to actually detect the edges. Okay, so we know that we have pulse like this and we want to detect edges. So what you need to do is you first differentiate it and remove all other information rather than edges. So if you differentiate, you will get the information of edges. So you will get this, and then what you will do, you will, because now you need to move this to upside. Okay, so but how can we move this to upside? So we know that the if we do full wave rectification, then in full wave rectifiers the characteristic is something like this. Okay, so if you pass this to full after full wave rectifier, so you will get this kind of information in time domain. Okay, so uh, so this is in time domain. So it is very simple to understand in time domain, but in frequency domain also you can see that we have sync function, something like this. Okay, and then you can pass it through edge detector and through your rectifier, so you will get spectral information at the edges. Okay, so this will be converted something like this, and you will get at the nulls, you will get the spectral information. Okay, so it is like spectral content at all the nulls. Okay, and then you can actually recover them. Okay, okay, uh, so this is one way of doing it. So but in practical, how to actually work on it. Okay, so let's look at edge detector, a simple circuit of edge detector. Okay, so you can intuitively, you have seen how it should be done, but in circuits actually how we should work on it. Okay, so so in circuits it is very simple, that what you can do is because you just need, here we have seen that we just need a pulses, something like this. Okay, we need a pulse information of each of the edges. Wherever there is change in 0 and 1 pulse, then you want a edge. Okay, so what we can do is, suppose this is data, so you apply another signal with a very minor delay. So this delay should be very minute, delta x, and if you apply this, then let's assume this is VA. If you apply this, then at the output, and if you somehow process it in a such a way that you will get this kind of so you can say that it is nothing but a edge detector. Okay, because you are getting a pulse, a very short pulse at each of the edges. Okay, so how to do that? So this is the circuitry that you can use. So first of all, here we can see that we want a 1 when we have 1 and 0. So the property is nothing but XOR only. When, so we know that in XOR, if we have 0 0 1 0 1 0 1 1, so we will have 1 1 0. Okay, so this is the XOR truth table. So we know that if there is 0 and 1, so we want a 1. So this is only by using XOR we can easily achieve that. So now and because the VA, if suppose this is VA signal, so it should be delayed by a small portion delta x, and this should be D. Okay, so simply we can design an edge detector. Okay, so this is one of the way of doing it. one of the way of doing edge detection. So can we use flip flop for getting that delay? Okay, or directly to get the face detection. So if we use flip flop in place of, so we will get Dean. Okay, so that anyway data we need to apply, and then suppose we have a clock that is anywhere. If this is coming, then the output will be based on the data. Okay, so I have taken something like this. Okay, so now this is one of the way of getting the delay. Okay, so can we replace the same thing here? So we take this, and to get the data or to get this particular delay, what we will do is we will replace this with clock. Okay, so this will ensure that you will have a proper delay. Okay, it will be based on the clock. Okay, so or we can use a simple waveform. Okay, and the clock edges will be at these points, so I mention it here itself so that there will be no confusion. Okay, so maybe I'm not good at drawing, but I think I have given the crux that in all those dots the pulse edges will fall. Okay, so Dean, and this is clock. So if this is VA, so the VA will be okay. So so the out will be something like this. Okay, so the out is the Dean X or V. Okay, so here you can see this is called linear phase detector. Okay, the problem here in this particular the problem is in this particular is it is very much depend on the data density. Here you can see that wherever there is fluctuation, based on that VA is actually operating. Okay, so the problem here is it is very much dependent on data density. Okay, so average value you need to find average value of out, okay, is function of data density. So this is the actually problem. how to solve this? Okay, so the solution can be two different phase error from different data density could have the same VC output. Okay, this is the problem. So we need to actually need to eliminate dependence of this data density. So what we will do is we will rather than using one of this variation, we will use two. Okay, two such kind of blocks. So let me draw the circuit and then we see. So DQ. Okay, so the as per the earlier circuitry, we have DN and there will be XOR as it was earlier, and it will be like this. Okay, there is no change here, so let's assume this is Y, this is B. Okay, then what will do, you will put another D flip flop, apply clock, and take another XOR, and then you do everything and get the VC. Okay, so if this is A, this is X, and this is Y, so let's again assume that similar kind of data we have, something like this, and let's again, I should represent in the form of dots to know the clock edges. Okay, so this is something like this. Okay, so dot are the clock edges, so that you will not get confused because of my poor designing of this waveforms. Okay, so if you look at B, so B will be delayed version of the D. Okay, so and that delayed version will be as per the clock. Okay, and there is A, it is half clock cycle delayed to the B. Okay, so the A will be half clock cycle delayed, so this is T clock by 2 difference from here to here, so the A will be something like this. Okay, so after getting this, if we do XORing of A and B, so here we have B, so we can get X. Okay, and Y will be as per what we have got earlier. So now X will be something like this. So this is X, so wherever there is change we will get a pulse. Yes. Okay, so they all are of same amplitude. Okay, and so A and B, there is very okay there, so A XOR B. Okay, so it will be something like this, something like this. Okay, and so this is X, and Y will be D in XOR B. Okay, so Y is D in XOR B, so it will be something like this. Okay, so I think it is not falling at the right window. Maybe I should use something like this. Okay, so this is a very short pulse of Delphi. Okay, so ultimately what will be the VC? This one, this is nothing but y minus x. Okay, so we will take y minus x for VC, and that will nothing but something like this. Okay, so here you can see there is area of for rise and fall. Okay, and so this is what we will get when there is no you can data and clocks are not aligned together. Here you can see that data is not aligned at the mid, so that is why you can see the mismatch in here upside and downside area. Okay, but in the logged case, so the logged case will be when the data is something like this, and the clock is falling at middle of it. If this is the case, then this VC will be the area of this both will be same. Okay, the upside and downside both will be of same area. Okay, maybe this is something like this. So okay, so the main point that I want to put is like the area upside will be equal to area of bottom side. Okay, so this is called hog phase detector, and because the scientist Hogg has invented this, so on the name of him, this is called Hogg phase detector. And when you take average of this, so in the logged case the average is 0. Okay, and the clock is aligned with the data at the center point. Okay, so but in the because still we know that this is only phase detector operation, but how to get a good clock also. Okay, because we need to generate the clock also, and then we can work on it. Correct. So this is done using a loop, and this loop is very similar to phase locked loop. So this is I0, this is I0, and there is R, there is C, there is one more C. So I will break up all these components in a minute. So just wait for a second. Okay, so we have already designed the phase detector. So the phase detector will give a signal here, and the another signal we will apply here. Okay, and these two will be connected, and there will be a D flip-flop, and there will be another D flip-flop, and data will be the corrupted data will be applied here, and the output something like this. Okay, and now this recovered clock is applied here. Okay, and the data we will take from here, the good data. Okay, so now you can understand that the good data depends on the good clock, and for getting a good clock we need to have PLL loop. Okay, but because we are trying to recover the clock from the data itself, that is why a common phase detector that is used in phase lock loop cannot be used here. In the place of that, there is different kind of phase detector. It is called Hawk phase detector, is designed and was put here. This is the Hawk phase detector, and in this representation we have shown that finally we need to sum them, okay, and then do averaging. But how to do averaging in circuitry? In circuitry, that can be done using you can say that integrator kind of circuitry, correct? So what we can do is we can pump a charge, or just take the charge back from a capacitor, and by connecting uh, a current charge pump, you can say that. Okay, so here you can see that this is a charge pump circuit, this is charge pump circuit, and this is low pass filter, and this is oscillator. This is voltage control oscillator. Okay, so this voltage control oscillator, so whatever data variation we do get here at this node, earlier we have used y and x, so it is y and this is x. So this switch will operate based on this output of y and x, and that will provide a change in signal, and that will convert it to DC using this capacitor, and that DC will be applied to voltage control oscillator. And because this is voltage control oscillator, the oscillator will vary based on this voltage, and it will again this feedback is applied to the clock of the D flip flop. Okay, this same clock. So if this clock is good, then data will be aligned properly, okay, or readjusted. Okay, so this is how this is called clock, and this is the complete loop of uh, CDR. Okay, so it is also known as type 2 single loop CDR, clock and data recovery circuit. Okay, but what can be the problem here? So one problem is, because here we can see that it is very much depend on the flip flop. Okay, but we know that flip flop may have a delay, so finite delays in flip flops will affect the overall performance. So there will be a finite clock to Q delay, let's assume. So it will change the pulse width of Y by delta T. Okay, so the Y will change by delta T, and that delta T is nothing but T clock to Q. Okay, and that results in phase error. This is one problem. So for low frequency it is fine, but at high frequency, so at high speed, this delta t could be can be a large fraction of t clock. Okay, so it can be a large fraction of t clock. Okay, and that ultimately degrades the jitter tolerance. Okay, and this jitter tolerance is nothing but j toll, it is referred as. Okay, apart from that, there can be another issue with this particular phase detector, that is, as we need to do averaging using charge pump, and if so it depends on the pulse x and y, as we have seen. So here we have y, here we have x. So what will happen at very high speed, there can be a dead zone where both of the switch are not operating, or both are operating, something like that. Okay, so at very high speed, there can be dead zone issue. Okay, when both switches are not operating. Third is, we ultimately take average, and suppose waveform is something like this. Okay, so when ultimately after this filtering action, we will get this kind of waveform, something like this. So these are the waveform that we will get. Okay, so the problem we can see here is that there is a finite kind of pulse, and this will actually result in change in oscillator frequency. Okay, because this small fluctuation, if you see, it should be ideally a straight line. Okay, but practically this is not possible to have a straight line. So it will give us variation in VCO. So because this is, we are going to apply in VCO, so VCO will be, if you have pure DC, then you will get a good, something very ideal kind of oscillator. Okay, oscillating waveform. But if this fluctuation will come in between, suppose there is fluctuation, small fluctuation here, then there will be a phase variation here. So wherever this fluctuation will come, there will be this variation. So it will be a little bit deviated, then again it will follow the same path, then it will be deviated, something like this. Okay, and this if in terms of eye diagram, if we say, then you will see the jitter here. Okay, this jitter will occur because of this fluctuation. Okay, so so there is one way of so people have thought of that, why can we get rid of this kind of problem. Okay, so they come up with binary PD. They say that, okay, why we need to work for full signal, why can't we take decision based on 0 and 1? So we need to find whether data and clock are aligned or not. Okay, so we can take a decision that if data is ahead, then we can say that it is 1, if it is not ahead, then we can say it is 0. Okay, so can't we do and can decide in this manner? Okay, so this is D, Q and Q bar. So we apply data here, and in the D we will apply clock. Okay, so this is V out, and this is plus minus. So let me quickly draw the waveform. So let's assume there is a small delay in data has appeared, something like this. So the V out will be based on the this, something like this. Okay, and so this is one way. If here you can see that okay, here you can see that data is behind, the clock is ahead of data. If it is in different way, then you will see there is change in the waveform. Okay, so you can say that ultimately if you look at the characteristic of this particular phase detector, then you can say that the V out and this with delta phi, okay, this variation you can directly decide based on whether it is early or late. So if this is V out is 1, you can say that okay, clock early. If it is 0, you can say that okay, clock late. Okay, so it is simply you can get it. Okay, and but can we do it in better way, because here only one pulse we are getting, but we know that in charge pump if we want to apply, we need to have up and down both the pulses. Okay, so that is why there is another architecture that is used. It is called Alexander phase detector, and also known as bang bang phase detector. Okay, so D Q D Q Q, so it is connected in this manner. So here it is opposite clocked, and this is clock. Okay, and then you will apply a data. This is X, and this is Y. So Y is S1 X or S2. So here it is S1, this is a signal, this is S3, and this is S2, and this is S2 dash, and D in is applied to both the series of flip flops. Okay, so this is S2 X or S3. Okay, so this is S3. Okay, so now in this particular architecture, this is called Alexander phase detector. And also known as bang bang phase detector. So here if S1 is here and S2 is here, and if S3, so it is like we are sampling 3 times, okay, for the same data, and we are looking into the data whether where actually it is with respect to clock. So let's assume this is the data. So you are sampling at the this edge, and this edge. So 3 times you are sampling the data, okay, and trying to find out where actually it is. So the second combination can be that if S1 is here S2 is here, and S3 is here, and this is how the data is, the clock is coming. Okay, so you can look into the this S1. So here we know that S1 XOR S2. Okay, so it will be S1 XOR X3 is equal to 1, and S1 XOR S2 S3 is equal to 0. Okay, this is first possibility. Second is S1 XOR S2 is equal to 0, and S1 S3 is equal to 1. And the third possibility is if S1 XOR S2 is equal to S2 XOR S3. Okay, so in all this possibility, if this is the case, when S1 XOR X2 means this one. Okay, this will be S2. Okay, so if this is the case, then the clock is late, and if this is the case, then clock is early. Okay, and if this is the case, then no transition has occurred. Okay, no data transition. Okay, so now you can see that here in this phase detector there is certain advantage that you are not actually not sampling in between, and also moreover you are actually sampling 3 times. You are re-verifying. So that is why this is also one of the most popular phase detector in CDR. Okay, and rest of the, you can say that rest of the block is kind of remain the same like PLL. Okay, so if you just look at the PLL, then in PLL whatever you see, so in PLL generally we have phase detector. So this phase detector is based on F reference. Okay, and then low pass filter, and then we have VCO. Okay, and then we apply the feedback to the phase detector. Sometimes there is a divide by n, but that is not always required. Okay, so this is the PLL block. So here if you compare it with CDR, so in CDR also, in the place of fref you will apply the data. Okay, and now again you have phase detector and low pass filter and VCO. Okay, and then you apply here, and in this particular thing you will also try to get the data out of it. Okay, clean data apart from the clock. Okay, this is the difference, and rest of the analysis will remain same as PLL. Okay, so the CDR and PLL are same in the analysis wise. Only the difference is the phase detector. In PLL there are different kinds of phase detectors are used. In CDR we have seen that there are 2 kinds of phase detector. First is binary phase detector or Hawk phase detector. First is Hawk phase detector, and then is Alexander phase detector. So this Hawk and Alexander is used. Okay. Alexander phase detector. Okay. So sometimes there are different kinds of loop which is used, like what they do is they can detect the frequency differently and detect the phase detector differently. So this is very simplified version of the clock and data recovery circuit, but sometimes what they do is they detect the frequency separately, okay, and then use charge pump, and there will be a shared VCO and a low pass filter. So it will be applied here. So this VCO output will be the input of phase detector, frequency detector also, and phase detector also. Okay, and there will be another charge pump too, and the direction of this and this. Okay, so this is called FLL plus PLL, fifth shared loop filter. Okay, similarly there are different permutation combination can be done. You can share this thing and put it differently, or share some other thing and tool. So the inventors have done different permutation and combination, and have seen the advantage and disadvantage of all these architectures. So there are plenty of scope of research in this CDR, and there is plenty of requirement in industry also for designing these kind of circuitries. Okay, so I think with this information I conclude particularly this session. So let's, okay, so Naveen, I am
Yeah.
stopped sharing.
Thank you, Dr. Mahindra, for that session on clock recovery circuits. Very detailed. Any questions from the participants?
Hello, sir.
Yes.
High speed is in terms of also device speed we need to consider device speed.
Device speed is a different thing. Actually, in generally what will happen that there are two aspect of research. One is that the people try to get high speed using innovation in circuitry, and another way is to innovation in device level. So if device are faster, then definitely your circuit will be faster, but that is totally different area of research. And this is different area of research where we innovate in circuitry to fast to get high speed in the existing technology.
Okay, sir. Okay.
Hello, sir.
Yes.
Yeah, I just wanted to know the eye diagram you have just recently explained. Is this because of ISI intersymbol interference?
Yes, it is because of inter-symbol interference.
Okay. And one more query. The XY waveform that you have recently explained, I can see the three different logic level in that waveform. One is 0 VDD and one more that is above VDD. Is that 2 VDD?
No, no, no. Actually, my drawing was not good. That is why you are not able to. But
Okay.
only two logic levels I was talking.
Okay. Only 0 and VDD, right?
Yes.
Okay, and one more thing, that line coding technique. Okay,
Mm.
what kind of coding technique is used here? It is NRJ or RJ? I mean, not
Uh,
return zero or return zero?
it is NRJ.
NRJ. Okay,
Yeah.
and what kind of modulation technique is used here? QPSK, PSK, or MRA?
In modulation technique, we have not entered into. So this is simple time domain waveform.
Okay, and one more thing, the analog equalizer block is this quite similar to the threshold comparator or something else is inbuilt in this circuitry?
No, it is different from the threshold comparator. Sometimes the threshold comparator is used for equalization, but that is very rare.
Right.
This all equalization is all, you can say, totally different. So in threshold comparator, you can say that Nowadays, because of pulse amplitude modulation, you can say PAM4 or PAM8 is becoming famous nowadays. So this threshold comparison is required, but in equalization technique and incorporating it in PM4 or PM8, it is very challenging. So now research is going on that area.
Okay, then I mean, what exactly the key element inside this block? I mean, I really would like to know. I mean, what exactly is inbuilt in this equalizer circuit?
In equalization circuit, it is maybe you have heard of the in your DSP classes, you heard of feed forward filters.
Okay.
FIR filters you must have heard.
Yeah, yeah. Right. Finally,
FIR, IIR filters. Yeah,
right.
so in digital domain, this is the equalizer. It connect as a equalizer if you design it properly. And in analog domain, if you look, then you can say that there are inductive peaking or capacitive peaking at the high frequency level that can be used as an analog equalizer.
Okay. Because it looks like very similar to the regenerative repeater like of thing. That's why I just inquisitively asked.
Yeah, some places because equalization has very wide area also itself. So some places regenerative techniques are also used.
Okay. Thank you.